actually have way more slides than I could normally give in this kind of session, so I'll probably rush through them in any case, but I wanted them to all be there for reference so you can look at them in case. And I'll, and if you're sort of nodding off, I will not take any offense whatsoever. Okay, all right. So OpenMP was designed to be a fairly simple and straightforward programming interface. And I don't know if that has been your experience, but you're allowed to share. We can show your thoughts perhaps a little bit later on. Right now, it's doing its best to not be so simple. And the exciting stuff is actually coming this afternoon when Calvin talks. So there's actually a huge jump from OpenMP 3, which is sort of, if you like, the basics that I'm going to be talking about this morning, to OpenMP 4, which has a lot of new functionality. The somewhat sorry or sad part of all of this is that OpenMP 4 is not quite there yet. In other words, the implementations are on their way, but not quite available, which means that you can't use it today with exercises. And we really would have liked for that to be possible, but unfortunately it's not. So it's just the state of things. However, it hopefully will be around fairly soon, so you need to know about it. It has a lot of features that I think are going to be important for high-performance computing in particular. So do take that seriously, even though you can't use it today. Do expect to be able to use it soon, and do expect that it will significantly increase the power of this particular programming interface. Okay. All right. So this morning, what I was planning to do is talk about the basics of OpenMP. So the standard features that you need to get going. I'm hoping that there are at least a few people here for whom some of that's new. Again, otherwise I will run through it. I need to go fairly quickly anyway, given the slides, given the number of slides. We have one short break, or actually the two short breaks for doing one simple exercise just to make sure that you've got everything, that you know where the compiler is and you can run it, and trying two very simple things. And again, if you've used OpenMP before, you'll find those trivial. We weren't sure whether you'd have had exposure to it before now. So I hope you'll bear with us on that. And obviously, if you'd like to experiment with other features, do so at any time and just try things out, especially if there's something that you don't know. Okay, so I'm sure that you've heard a fair bit about architectures already at the start of this course, but in terms of high-performance computing systems, the big changes now and in the foreseeable future are actually inside the individual nodes of the large machines. And we have there, again, not only much more concurrency, so we have cores, and we have a growing number of cores. We have heterogeneity, so there are different kinds of cores, and although there are different viewpoints on that, most people expect that that's something that will be not only here to stay, but here to grow, at least on some kinds of platforms. Challenges with using memory, because if you have more compute power and the memory, in fact, the memory problems kind of grow even further, both with respect to the bandwidth, but also the power cost of accessing data. So there's no free lunch there at all, and you have to think very hard about how much memory you need and try to conserve it. Okay, so in this scenario, obviously, the application or the application developer needs to be sure that they're really using the resources on the node wisely. And one of the ways in which you can try to do so is to use OpenMP. OpenMP, of course, doesn't come without a cost. If you're doing high-performance computing, you're most likely using MPI. When you use OpenMP, again, then you're using two different programming models. That does make things more challenging, right? So this afternoon, when you talk about things, there are a few slides on sort of the pros and cons of doing this. And so it's again, something that's if you have performance problems or if you have memory problems, very much worth trying, but it's not the only way to go for it. Okay, so Rusty's already talked about what OpenMP is, just very, very briefly, and I'll say a couple of things. So it started out actually being touted as directive-based, so directives, instructions to the compiler, if you like. It's sort of the back door if you're not trying to change the language, but still instruct the compiler to do something, for shared memory parallel programming. Today, it's actually, or its mission is not to simply provide an interface for shared memory parallel programming. It's gone beyond that Today, in the morning, we'll talk only about if you like, the old scope of it. This afternoon, you'll hear about features that go beyond shared memory programming. So it's changing both in its mission and in its goal. But it is firmly based on an approach that allows you to use directives to influence the parallel, or to get the implementation to help you create parallel code. And the idea of all of that is that you want to make it easier. So as Rusty said, one of my goals, it's not my only goal in life, but one of my goals is to help make programming, or parallel programming, more productive. The idea of this is that the user makes important decisions but doesn't have to work through all the details. It's obviously less error-prone that way, and hopefully is easier for the application developer, tends to also increase portability. Okay, and the extent that you'll see this morning is all regarded, or is designed really to support shared memory parallel programming. That's its heritage, and again, it's moving on from that. One of the important things about OpenMP is that it aims to provide the same features for Fortran and C and C++, so Fortran and C dominate. I'm going to use, with simple examples here, sometimes I'll use Fortran, sometimes I'll use C. The intent is to provide the same functionality so that if you're going from one programming language to another one, you don't sort of suddenly discover that you have a whole different set of features. Obviously, things don't always look absolutely the same, but it's as close as possible. Very, very important. It's actively being developed. Very important. Okay, so where does OpenMP come from? This is the only history you'll see today, as far as I know. It actually does have a little bit of its own history, if you like. As some of you might already know, in the 1980s, there were some systems designed that had shared memory parallelism and were used for scientific computing. They died out pretty quickly when people discovered it was much easier to create or larger systems using distributed memory, so they didn't have a very long shelf life in technical computing. They did continue in some other areas. And for those systems, there were some early efforts to try and create a standard, or a de facto standard, as we like to say, but actually both were tried. Programming interface to allow people to, in those days, add some directives to Fortran codes to express the parallelism in them. Some of that actually got a little bit wild and woolly, but it was an interesting starting point. None of them were actually really used. Anyway, so when OpenMP started out again, which was in the late 1990s, so it's actually getting kind of old itself, it picked up from these early efforts and took them and actually extracted the best ideas from them to create the very first version. And partly because of that, the very first version also was targeted Fortran and was focused very firmly on allowing you to parallelize loops in your program. So that was historical, if you like. What's happened in the last 5 years in particular goes way beyond the ideas that were in those days, but the first couple of versions were still very firmly founded in that early work. Okay, so again, this is a little bit repetitive, but the initial version was for Fortran, then the features were adapted to target C in particular. There were some discrepancies in those different ones, and so there was an effort to actually combine those things and clean up the spec and make sure that everything was consistent. And there were some extensions that I will talk about at the end of this morning in version 3, and then 3.1 made some minor adjustments, which are a couple of years old. And the very big leap was version 4, which was actually released as a specification. As you can see, it's almost exactly a year old now. Because it's significant, there are partial implementations, but there are not yet full implementations. And again, as Rusty said, there is a website that you can go to look for information. There's a lot of stuff up there, including some good tutorials and more background information if you want them. And it's just at openmp.org. Okay? So feel free to go and look at that. You'll find lots and lots of stuff there. Among other things, you'll find the full text of the specifications there. As I said, OpenMP was designed to be simple. So if it sort of looks and feels simple, it's not that you're not getting something. It's trying to be as simple as possible. OpenMP 4, I think, goes way beyond what we had before and is arguably not so straightforward anymore. And the specification for it has over 300 pages. So version 1, the specification was kept very simple, and it was actually intended to be a document not just for implementers, but for people like you who wanted to use it. I think now if you look at the spec today, it's not quite as bad as reading the Fortran specification, but it's getting there. In other words, it's becoming more opaque and I think harder for the user to understand. So it takes a little bit of effort, but it is accessible. And if you feel up to that, and if you'd like to look at it, you can certainly download it. There are, of course, a lot of as with many other things, there are lots of rules and restrictions on how to use features. Most of the time, the restrictions are things you'd never think of doing anyway, right? But if you need to check it out and find out whether something is legal or if there's a problem, it is readable enough that you can go to the spec and I think get that information. Okay, so this is, I think, very important. So one of the goals of OpenMP is to make parallel programming, and again, specific focus on shared memory programming and certainly still intranode programming as easy as possible. The other goal is for it to be portable. And that's not easy. OpenMP requires a compiler. A compiler implies a lot of investment effort on the parts of the vendor. Right? So for all of its perhaps strong and weaker points, one of the things that has worked very well with OpenMP and now for quite a considerable amount of time is that the vendors have collaborated and agreed on a set of features, and they're providing implementations at roughly the same pace. So that's actually very, very important, because obviously if you're creating code somewhere, you don't want to go and rewrite the entire code for your next system. And so this is, again, is its very big strength, I think. Membership changes a little bit. Obviously, companies come and go a little in this field. Just one or two things that I wanted to mention here. Sorry, this should be ST Microelectronics, not Saint. It's not a Saint. We don't have a Saint in there yet. Well, maybe we do, but we don't know about it. We actually have a lot of, quite surprising for me, a lot of interest from the embedded systems community, and had a lot of interactions with them over the last year or two to try and see how they can use OpenMP and how it fits in and suits their style of working or their ranges of applications. Important because you don't just want a portable programming interface, you want one that has a big user base and is around. Makes a big difference in terms of getting tools and support. So as the embedded systems community starts to use OpenMP especially for their high-end devices, the user community is going to grow a lot, and we hope that will translate into much more support, much better support. Right? So it's not just about having support, it's also about the quality. So you can do a quick and dirty implementation anytime, but doing a good implementation requires commitment and effort. And we hope that that's going to continue to increase the pressure, I think, even on vendors to do a really good job of providing OpenMP. There are also some auxiliary members. I just highlighted the ones that are represented today in the presenters. So I have kind of two hats. Some of those you see here, Argonne is a member. This is Barcelona Center, Los Alamos, Lawrence Livermore, and Sandia, and Berkeley is also in the process of joining. So quite a few of the labs have joined in the last few years, and partly because they've been increasing, I think, perception at least that there's a need to do something more than MPI for many applications within the nodes. So they're very much involved in that as users more than anything. Okay, just a photo from a recent meeting. So this was in Houston, and just to rub it in, this was in the middle of winter, so it's a bit, all right, a bit warmer down there than it was up in Chicago, I think, last winter. But so people are very busy working on this still, and that's, of course, important to try to keep it relevant. Okay, so I'm going to go on now and talk about the basic features, and I hope for many of you, or at least I'll put it this way, it seems like for many of you this is going to be just a very simple reminder of things. I hope there are a few people for whom this is perhaps a little newer, but think it's important for us to go through them in any case. Okay, so the idea again is OpenMP provides thread programming interface, so it assumes that a program is going to be executed by a collection of threads. It tries to do that at a reasonably high level, which just simply means you as the application developer don't need to say absolutely everything. You don't need to spell out all the details. So in particular, the threads are going to collaborate in some way to execute the program. You say, again, how you want them to do that, but you don't give all of the details. All right. The threads, this is a slightly MPI-centric way of looking at things, because what I've discovered is that people who start out doing MPI sometimes slightly misunderstand OpenMP when they first try it out. It's a little different. It's not, it's not different, but just a little different way of seeing things. So in MPI processes, of course, you have to have communication between them to transfer data. You don't have to do that here because you have assumed that data is shared. So how do you communicate, if you want to think of it that way? Well, you just have shared variables, right? They read and write. However, you have to, of course, be sure that if you want to use some data that was created by one thread, you want to be sure that that data is available. So you are going to have some synchronization to make sure that that happens. So that's the challenge. Okay. The other thing that OpenMP, with some exceptions or some features that don't follow this, but by and large, it emphasizes structured programming. So try to keep things, don't have crazy jumping in and out of features to reduce the likelihood of programming errors. And even though that some of that seems kind of obvious today, and you would sort of say, well, why would I do anything else? Some of these very early attempts to provide shared memory programming had things that seemed kind of crazy to us now. So they would allow you, for example, to create a parallel loop and to jump in and out of it. Well, they tried to allow that, which was one reason I think that they didn't go anywhere. But that kind of thing is not supported in OpenMP. Well, if you're trying to use the features of your node successfully, what would you do today? Obviously, we're presenting OpenMP here today because it's one way in which you might be able to exploit the cores in the node. You may be just fine with MPI on its own. All right, so don't ever write off MPI, and I'm sure Bill will tell you that later. POSIX threads can also be used. They are lower level, so we just have one comparison today just to sort of make that point. So you have to say a lot more if you like. You get less support, but it tends to be available. Libraries actually have a little bit of a hidden defect, in fact, and that is that because it's a library, it doesn't tell you things about that you actually would like to know, at least if you're working. If you're working and you want correctness, you want to know actually when data is available. You want to know what your memory model is. When is data updated? A library can't tell you that per se, so it has a bit of a defect that way, but it's very powerful and has some other options. Most vendors have worked quite hard to provide automatic parallelization for multi-core systems. Why? Because obviously there will be plenty of people who would like to create parallel code who do not want to do anything at all. So it tends to be there, but I don't know if anybody has tried it and had a different experience, but usually we don't expect to get too much from it in terms of performance. So usually automatic parallelization can only handle very, very simple problems. So it tends to not be a solution for HPC. Okay. All right, so OpenMP has, and again, we're not going to 4.0 today, or at least this morning, it's coming this afternoon, has a collection of directives, and if you've used these before, you'll already know that they are pragmas in C. No, it's recast as pragmas, and they're simply comments in Fortran that have a specific structure to them. There is a user-level runtime library, so things that the user can use to either get information or set some values. And there are some environment variables that help you control the overall operating environment. So those are the features. The most important ones from our perspective are the directives, because those are the ones that tell the implementation, so the compiler in particular, what it needs to do. So what it has how to translate the program. So obviously the main role of the user is to insert those directives. That's what you do, right, when you're creating OpenMP. But while you're doing it, you also have to make sure that you do not introduce bugs. So one of the perhaps minor caveats of using OpenMP is that the implementation expects you to create correct code. In particular, if you're trying to create a parallel loop and there are dependencies between different iterations, it's your job to remove them. The compiler is not going to check. It's going to assume, in general, that you have written correct code. So you have to make sure that what you're doing, in other words, is correct. Okay, so one of the good things about OpenMP is that nowadays it's very easily available. You'll find that if you're using GNU, it's there. GNU has some good parts and some not very good implementations in some areas, but it's there. Most of the time, again, the standard compilers that you use will provide OpenMP. You don't need to go and get anything separate, but you're going to have to provide a specific switch. And they're not standard, so they're slightly different depending on the compiler that you use. So you'll have to look at the manual to find out what switch to use. Sometimes you have to also set an optimization level. So you might discover that you have to put this particular switch or flag and 03 or something else to make it work. We'll come back and talk about stack size later. Just in case anybody's very interested, there's a small group of us right now working to try and get this into LLVM. So the LLVM infrastructure has not supported OpenMP to date, and Intel and IBM and my group are working to change that as we speak. So that's coming too. Okay, so the idea of OpenMP is that you can have a program with OpenMP annotations in it, if you like, so the OpenMP directives, you use in your compiler. And if you don't use those switches, you have a sequential program. If you do use the switches, you have a parallel program, which is great for maintenance. This doesn't work without some care. In other words, if you're using runtime library routines, then you might have to use if-defs and so on to actually make this work. But in principle, at least, you could actually have one source code that's both sequential and parallel, which actually can be quite important for vendors. But again, you have to take some care to make sure that everything would actually run without the OpenMP flag. Okay, so to wrap things up, the end user creates the OpenMP application, of course, sets the environment variables, may also use library routines. There are some directives that are translated by the compiler, and the compiler, we're not going to talk about the implementation today, so sometimes we've given tutorials and focused more on this part of things, just to show how it actually all works under the hoods, but today we won't have time to do anything much there. The compiler usually relies quite a lot on its own runtime system, which is not the user one, and interacts, of course, with other elements of the environment. All right, so I'm going to run through the main features this morning, or at least in the first session this morning. I'm going to try and go through the first three things here, so parallel regions, work sharing, and synchronization, which are somehow the basics of OpenMP, and hope that by the end, or by the break, that we've gone through the most important features there. Okay? All right. So what's the whole idea of OpenMP? So OpenMP starts execution like any good process. Since a process running, it will start with a single thread. And that's usually called the initial thread. And it also becomes the master of any teams. So when you as the application developer tell this program to go parallel, then this master thread is responsible for creating a team of threads. First difference with MPI, you don't always have parallel execution, right? So if you are in a part of the region part of the code that's not parallel, then you actually have sequential code, and you're using one core, not how many you have, right? So obviously you want to try and spend as much time as you possibly can inside parallel regions. Okay, so here's the master thread. The initial thread becomes the master. The master thread, when it's told to, will create a parallel region, so it's creating all these new threads. The master itself participates in the execution of the parallel code in that region, so it doesn't disappear or wait, it's part of the team, and collaborates with these worker threads to do whatever it is that you ask to do. At the end of that parallel region, there's a barrier, and the barrier is where all of the threads, if you like, come together, wait for each other to complete, and then they will proceed. And this could have some sequential code in here. Again, remember that not everything is necessarily parallel in this environment. So there could be some sequential code here, or you might dive straight into the next parallel region. Next difference, there's a certain amount of dynamic behavior in OpenMP that you can also influence. So notice that this parallel region has a different number of threads. So you can change or allow the system to change the numbers of threads that execute the parallel regions. So that's something that can also vary. So in other words, if you had perhaps not enough work over here for more than 4 threads, use 4 threads or 4 cores if you like, probably. And then you've got more work over here, so you grow that number. Right? So you can adjust to the workload. All right, we're stopping here. Then as another parallel region starts up. And inside this one, we've got another region inside in the middle here. So another thing that you can do here is you can actually nest parallelism. So you can have some teams working, doing some work, and one of them perhaps has a very heavy workload in principle. If you've programmed this way, of course, you can create another team of threads to do something else. So that's another thing that's a little different here. Okay, so these, I've already used that word, these are called parallel regions, and they're blocks of code that are going to be executed together in collaboration by all the teams in the thread. Okay, yes?
Quick question on the nested parallel regions. So
yes.
One of my coworkers mentioned that they had trouble with the nested parallel, that the implementations didn't necessarily support that very well.
That is correct. Okay, well, we might want to leave that to the afternoon. You might want to perhaps ask specific questions, but I had some slides right at the end of the morning to say a little bit about that, but it doesn't, first of all, I'll say what I'm going to say then since this came up now. First of all, the implementations don't have to implement it. There are, even though this is portable, there are a bunch of things that we will remind you of that are implementation defined and a few things that are optional, and that's one of the few things that are optional. It was also actually, the initial support for nested parallelism was, I would call primitive. It didn't have much expressivity. There's been a lot added to that in 3.1 and some more in 4, and I think that's changing the power of it. And I think both as it's more usable for the application developers and more expressive, and as the core count grows, I think it's going to be, and Calvin can feel free to disagree with me later, I think it's going to be a lot more important for the implementers to provide good solutions there. So I would expect that to be something that's changing. What you have to remember in all of this, even though these things are in some ways quite simple, the effort that you have to go through here to get all the implementers to actually agree on this and put it in the compiler is much, much higher than it is with providing library routines. And so some of the time you'll find that the features that are not deemed to be very important are not necessarily all that well implemented, and that's obviously changes with time. But thank you for asking that. So, okay, important point, you create these parallel regions. There is a certain amount of dynamism in there, a certain amount of flexibility, if you like. You can grow things by either changing the number of threads or by introducing a new region. Those threads will come together at the end of the region, and then you go into the next phase of computing. The other very important basic feature, if you like, or basic principle of the OpenMP is its memory model. And this, again, this is at heart, it's a shared memory programming model. Again, Calvin will talk about other things this afternoon that break this a little bit. But at heart, it's a shared memory programming model. So if you want threads to collaborate to do something, they do that simply by using this, referring to the same data. It is the same data. It's shared data. However, data can also be private. So threads can have their own view of their own local copies, and I'll call this local sometimes, copies of certain data. So you can say that I've got 6 big arrays in my program, they're all shared, and I've got these half a dozen variables that I want the threads to have their own copies of. You might do that for performance reasons. You might do it because you really do need the threads to have their own values of certain variables, all right, to influence how they're actually computing things. Okay, so having it private is both helps expressivity and also helps performance. But private really means private. It's only accessible to that thread. So each thread has its own individual copy, and the values can be quite different. It's designed to be that way. Okay, and you don't, again, this is sort of here for an MPI programmer, you don't put in any communication per se. You have to make sure, again, that you know when data is available, but you don't put in any communication statements in this model. Okay, so I think I've actually said all this. So we have data is either shared, that threads can read and write it, or it's private and nobody else can access it. The only thing I didn't say before is that the default is shared. So if you don't, with a few exceptions, there are a few specific kinds of variables that have to be private, but with just one or two exceptions, data is shared unless you say otherwise. Okay, so the syntax is pretty simple, I think. So in C, we have pragmas. So you use that pragma and use the OMP symbol, if you like, to introduce them. So they all have that on. Fortran has a couple of different forms just to take account of the fact that there's, if you like, old Fortran, Fortran 77, and more recent versions have different kinds of comment options. And all of those are OK, and you can use them. And the compiler will recognize them if you've used the right flags. If you want to use the runtime libraries, you're going to have to also have an include file. And so that's just mentioned here, too. I'm not going to go through this at all. I'm taking this for granted, and I assume that since nobody's over 100, I hope, in this room, we probably all prefer structured programming anyway, but there were days and times when people did not necessarily think very hard about the control flow in their applications and jumped fairly wildly on occasions into and out of regions. So OpenMP requires structured blocks. So in other words, if you have a parallel region, you do not sort of jump out of the parallel region in the middle and jump back in again, or the same thing with the parallel loop. So we just take that for granted. You start at the top, you exit at the bottom, with just this exception. OK. So diving into an example just to see these things sort of in the middle of things. Here's a piece of OpenMP code, and you'll see that the colored portions are the, if you like, the OpenMP syntax that's been added to this loop and the print statement. All have the same sentinel in this case. We've created a parallel region. The first part here, OMP parallel, is a directive. The default, and in fact, everything on the next line as well, are all clauses. So we have a fairly small number of directives that instruct the compiler to translate something in a specific way. And there's a certain amount of information that you can add to each of those. So each directive has its own set of clauses that can be used. A lot of them actually have to do with the data that you're using. So we'll see those later. And this particular one is a reduction operation. And so it's, actually, before I say that, sorry, this was Fortran deliberately. In C, you kind of have natural blocks, right? So curly braces, end your region with curly braces. Fortran is not necessarily like that. So in the Fortran version, we have start and end portions to the directives. So we're going OMP parallel and OMP end parallel, and the same with do. So that's a slightly different just because of the nature of the languages. OK, so this one is actually a parallel loop that's going to be performing a reduction operation. We'll come back and talk about those a bit later, so just sort of have a non-trivial example here. One of the things you have to always know about in OpenMP is when are the results available? When is the data available? And for a reduction operation, that's actually going to involve the entire loop, so the results won't be available until the end here, until after they've all synchronized and come together. So, so there are a few things that you have to be aware of in terms of the availability of data. OK, so we're now going to go in and go through these features and make sure that you know them. Just a few basic things now about parallel regions. So parallel regions are kind of the most fundamental directives in OpenMP because if you don't have a parallel region, you don't have parallel execution. So parallel region is where you create a team of threads, start them up, and give them some work to do. OK. So remember we had that picture where there's a master thread. When the master thread encounters a parallel region, it creates a team of threads. In practice, it actually often wakes them up if it's not the first one in particular. And those threads in particular, so that we can access them, are going to be numbered. All right, so this is a programming help, I guess, in some ways, but the threads are numbered starting, so 0, 1 through 3, so in positive ascending order. And the master thread, it always has thread ID of 0. Right? That allows you to actually, specifically as an application developer, to address those threads if you want to do that. OK. I said before that you can actually dynamically vary the number of threads in a team. Important to note is that you can't do that in the middle of a parallel region. Right, so you start a parallel region, you have a certain number of threads for that parallel region. That number of threads will execute the region and terminate. After that point, you might be able to influence, or the system might influence the number of threads that the next region uses, but you don't change the number of threads in the middle of a parallel region. Once you have that set at the start of the region, then those threads will be that team, and they'll continue to the end. Okay, and this is the question we had before. So the nesting of parallel regions is somewhat implementation dependent, and it doesn't have to be present. So you need to, if you want to use that, you have to test your implementation and find out what it does. Okay, and because you don't always know, now this is sort of jumping into a performance issue, although we're not going to say much about performance this morning. You don't always know whether there's enough work to justify parallel execution. There's also an if clause. So when you say there's parallel, you can also put if there with a condition. And then depending on the value of that condition, the program, or at runtime, it will either be executed in parallel or sequentially. Right? So that's evaluated dynamically.
When you talk about thread adjustment,
yes.
And it has to be done outside of a parallel region.
Yes.
Mm-hmm. Can the adjustment be done based on how loaded your machine is?
Yes.
Can the OS influence, hey, I've got a lot of work here, so yeah.
Yes, the idea of dynamic adjustment, so there's two things you can do. You could specifically change it yourself using a library routine. Say, I want this number of threads now. Or you can allow the system to do it. And the goal of allowing the system to do it is to try and optimize its use of resources.
I would assume that is more or less dependent on the implementation,
How it would do that, the details, yes. Yeah.
Would you care to comment on how generally the performance is, or how good the implementations are as of today, maybe?
Do you want to say something about that? Well, it's okay. Would you like to say anything, Calvin, or?
I think it really depends on the implementation, as Barbara said about that. As for example, in the IBM's implementation on BGQ, that's the machine data, because we already have the 64 threads, that's the limit. And also our implementation by default is just pick up the number of available processes. Okay, so there's a possibility that you are using 64. I mean, in non-BGQ system, you're using say 64. I'm using 64. They will oversubscribe the system. So that is there's always a balance in between that. Whether you are running your application as dedicated machines, or running your system on non-dedicated machines. I think this is all is kind of a little bit complicated issues.
I was going to say a little bit about that in a different context, so maybe I'll just say it now anyway. So assumptions in high-performance computing, we tend to assume that we have a machine that we're using, we have access to. There are other, obviously other implementations and scenarios and sort of more general-purpose computing where you cannot make that assumption. And the defaults that you tend to use there are different from the ones that you would use in HPC. And you'll see that. So GCC, for example, assumes more system noise and actually has different defaults because of that. Right? So they're very different scenarios, if you like. But the idea, so that it's like a number of other things, and I guess this is unsatisfying in some respects, but OpenMP as a specification is often a little bit fuzzy in order to allow implementers to do what's right for their environment. And that does depend somewhat on the kind of platform that you have. So yeah, I'm always a little reluctant to say too much about other people's systems. And in HPC, the other thing is that at today, and I'm not talking about tomorrow where things may well be different if we believe what we're being told. Today, we tend to like to control things. So we want to go we tend to want to figure out exactly what we need and maybe experiment until we know what it is we want and then actually use it. So that's the way we've usually used it, and that's why I personally, in my work, I wouldn't use dynamic too often. But okay, so we tend to want to experiment if we know our application and figure out what thread numbers we actually want and set them ourselves, rather than just leaving it to the system. Okay. Okay, so how to create this parallel region, or how to do that from the user's perspective, very simple. You need to know about the parallel directive, or pragma. So essentially just this one line of code. So what we've done here is we're telling the system what we want. We want 4 threads, and this is the parallel region. And we expect now this code to be executed by the team of threads. So that would be the master thread and 3 additional threads. So not 4 additional ones, but 3. So altogether 4. And here we're also using another of the library routines that are available to the user, which will have each thread retrieve its own thread number. So remember, we said threads have an ID starting at 0, so each one of them will have one, but they'll all be different. So for these 4 threads, they will have the IDs 0, 1, 2, and 3. Okay? So guess what? This is a private variable because each thread has its own copy of that one. Has to be. All right, so each thread will get its own ID, and then each thread is going to execute this procedure. Do they all do the same work? Well, without seeing the procedure, I can't really say, but notice that each one is as an argument, is using its own ID, so there's at least a chance that they're actually diverging and doing something underneath based on that. And so in a sense, when I say it's executing the code redundantly, they're all calling the same code. They're executing the same code, but because they have their own value there, they could actually be doing something different. A is shared data, so they all have access to A, to the same array and the same values. Okay, all right, so threads are set up, enter the parallel region, do that work, whatever that work is, come back together here, and print is just sort of saying, okay, it's all over, we've done our job. Okay, so that's the fundamental step in OpenMP. The parallel region enables you, or directs the master thread, if you like, dynamically to create the team of threads. The threads will all do whatever work is inside the parallel region, and then they'll end. That's it. So is it simple or what? Okay, so it's very, very easy. And again, you can add a clause to this one in particular that will tell the system whether or not you want it to actually do that. So even that step can be suppressed if there's not enough work and in the actual thing. So very early, this is not relevant to you, but very early attempts to provide these kind of directives required all of the work to be in the lexical extent of this. So for computer scientists among you, that means that anything that was going to be parallel, any directives had to actually be literally between these two, the start and the end parallel directives. That's not the case with OpenMP, and that's extremely important obviously for being able to write sensible code. The extent of the parallel region, and this is what you would expect, so I'm just telling you that you're getting what you would expect to get. It just was a change from history, is that you can have, obviously you can call all kinds of different procedures inside the parallel region, so in that structured block. And you can have directives inside them too. So you can call procedure after procedure and still have OpenMP features inside the rest of your code. So again, I hope that you take that for granted, but the past was not like that at all. Okay, so you have to sort of start with hello world if you have C. So just one simple hello world example. Again, very easy to write this in OpenMP. We've got our include file here because we're using a library routine. We've got our parallel pragma, which is going to tell the master thread to create a team of threads. And since we don't say anything about the number of threads here, we get what we get, right? Which will be whatever the system decides to provide us. And that, again, may not matter sometimes. In HPC, it tends to matter. So we tend to want to actually set things more actively. Okay, so we're going to retrieve the thread ID, and they'll all print out hello and then world. And of course, because they're all threads and they are executing asynchronously, and we don't quite know the precise ordering of things, the order in which you get these, well, it will vary a little bit, right? So if you tried to run this, you might find that there's something skewing the system a little bit, but in most systems you would find that the order in which things were printed out would change a little bit from one run to another, right? So there's a certain, if you like, randomness in all of this. Again, on some kinds of systems, if there's a lot of system noise, you might find that one thread's real slow. You tend, on an HPC system, you'd like to think that that won't happen, but it's possible. So I'm going to race through some features of OpenMP now, so literally go very quickly through the following slides just so that you've seen these, and I hope that they'll be reasonably familiar. So the first thing that you've done is really see that there is one style of programming in OpenMP which relies a lot on the library routines. You can do that. You can use your thread IDs to actually share or to instruct the threads to do something specific, or to, as that example showed, to carve up the iterations of a loop among the different threads. And sorry, let's go down one further. So doing something like this. So we had this is by the way, this is another parallel loop with a slightly different strategy for assigning the iterations of the loop to the threads. This one, actually each thread has its own chunk of iterations. Each of these you can manually create. It's not terribly difficult to do. And that way you have full control over the work that's being performed by each thread. So that's one style of programming. We tend to call that the SPMD style, where you're using those things to actually do that. But of course, this kind of thing is very, very common. So if it's common, you'd like it to be easy. And to make that easy, OpenMP has another directive, which is an OpenMP do in Fortran, or an OpenMP 4 in C, which tells you, tells the implementation. You're telling the implementation that you want this to be executed in parallel. And the strategy that OpenMP uses here, again, I hope it's the obvious one, but there have been language attempts that did different things, where it's the iterations that are being mapped to the threads. So just as before, each thread will get a subset of the iterations. That's partitioning the iteration space, if you like, and each thread will do a portion of the work. And you can actually, so stand here, you can actually just say OMP4 and let the implementation decide the best way to do that. Or you can give a schedule. The schedule is the word that's being used here, which allows you to tell the implementation how you would like that iteration space to be carved up. All right. So in the early days, OpenMP focused very heavily on loop parallelism, and this was the main feature after the parallel directive. So an OpenMP do or an OpenMP 4. And I think we've said all that before, and we tend to talk in our OpenMP space about chunks of work. So each thread gets a chunk or perhaps a couple of chunks of work. Something we didn't say before is that at the end of an OpenMP 4, as well as at the end of an OpenMP parallel, there's what we call a barrier. So the threads actually, when they execute a parallel loop, right? So a parallel region can have one or more parallel loops. There could be a series of loops inside there, right? At the end of a parallel loop, there is a barrier. That means that the threads all do the work in that loop, and then they wait for everybody else to reach the same point, and then they proceed. If you don't want that, so waiting can potentially be expensive. So there's a way to suppress that. If you don't want all the threads to wait, you can use what we call the no wait clause. And I'm going to repeat that a little bit later, but I'd like you to see that here now too, so that you have a wait in there by default. If you don't need it, you can suppress it. Okay, so in other words, an OpenMP 4 loop executes, you all come together, and then you execute the next one, unless there's a no wait. Okay, something else that you need to know about the OpenMP 4 and the OpenMP do is that the implementation to do this, so one important comment, each thread, you probably haven't thought about this too much, each thread is able to compute its own iteration set. That's important, right? So if the threads don't have to handshake or agree with each other on what they're doing. Each thread can figure out its own set of work, and doesn't have to influence the others. To be able to do that, there has to be known before you start this loop. You have to know how many iterations you have. And that puts some restrictions on the kinds of loops that can actually be parallelized using this way. So we tend to say that there has to be the iterations have to be countable. So there are some kinds of loops that you can write in C in particular that do not follow this stratagem. And we'll come back and talk about those later on in the morning. So if you have in particular a loop that's traversing a link, if you're traversing a linked list or something like that, you can't use the OMP4 on it. Okay, so we'll just say that now and move on. Okay, another thing is, what if you say, well, I really would like to parallelize multiple levels of a big loop nest, right? So I've got lots of work in here, but really just one loop level isn't enough work. I've got multiple levels that are parallel, and I want to do that. To do that in OpenMP, you have to use what we call a collapse clause, and that actually operates on some loop levels that immediately follow each other. So if you look here, you've got this one says parallel do with collapse 2 that says parallelize the following 2 loop levels. So that's the I and J here. Okay, so OpenMP will create, if you like, combine those to create one big iteration space, and we'll parallelize that. We'll map those to the threads. So you can, yes, you can parallelize more than one loop level, but you have to do it this way.
So you said immediately after. It's a very common programming style to, at least in C, dereference immediately after nested loop or immediately before nested loop. So can you still dereference something to memory and take advantage of this collapse, or should we change our programming style just to do loop after loop after loop?
I'm not quite sure if I got your question.
So is it possible to include code before your second due?
Oh, I see. Okay, no, it isn't. Actually, there was a lot of discussion about that because, in principle, there are lots of different kinds of loop nests where the compiler could actually do the translation, but there are also plenty of cases where it can't. And it was too hard to actually describe the defaults in any sensible way to the user, so we decided to keep it simple. And so, yes, there's not allowed to be any code between them. So they have to be, if you like, tightly nested. Yeah. Yeah, and again, it's an implementation issue, and I think the consensus was that allowing more is possible, but it would be very hard to explain to any user what the rules are, so it was kept simple. Okay, so what are those schedules? So the schedules are not about correctness, they're about how the iterations are mapped to the threads, which might influence the performance, all right, so rather, but should not implement the correctness. So here's what OpenMP offers you. It offers what we call static, which is going to give the different threads chunks of work, so fixed chunks of work. It could be just one chunk, so each, in that case, each thread would get one contiguous set of iterations, often good for cache. Or it could be, or there could be multiple. So if you have you can also specify a chunk size. So if for whatever reason you want threads to get 100 iterations each, and then another set of 100 iterations, you can specify it that way. Dynamic is a good idea if you have a workload that varies some. So if you have a dynamic schedule, then each thread will grab a set of iterations, and when it's done, it will go back and get another set. So if one thread is much faster than the others, for example, it will pick up more work this way, and you'll hopefully have better load balance. Guided is similar, except that it starts out with bigger chunks, and the chunk size decreases over time. So it's if you like, a variant of dynamic. Auto is actually, it's not really a schedule. It's saying let the implementation decide what to do. So we found, at least in our own, obviously we have research implementation, so we like to play with things, and we found that there can be quite significant differences among different applications and systems in terms of what actually works best. So this one is letting the runtime use whatever it can to make this decision for you. And last but not least, if you set a runtime schedule, that means that you're going to actually set the schedule dynamically, so you can influence that. And there are library calls that will let you do that. Okay, so if we have a static schedule, this is no chunks. So again, as in many other contexts, you don't want, first of all, you do not want to rely on the schedule for correctness. You should not be, your program should not bomb out if the schedule isn't the one that you thought you were getting. But there are, some of the details are left to the implementation. So if you had 4 threads and 16 16 iterations. The top line is what you would, what you would expect to get just by saying static schedule. If you set the chunk size to 2, then it's a little bit of a round-robin approach, right? So the first thread would get, so the master thread, if you like, would get iterations 1 and 2, and then it would also get iterations 9 and 10. Okay, so just so you can see that difference, if you have a static schedule, this is, again, just something arbitrary. You get static with no chunk size. Each thread will get 1 block of iterations, so this is the red stuff at the bottom. If it's dynamic and you've got a chunk size, you'll see that there's lots of little pieces of work, and each thread is going and grabbing another piece of work when it's done. And with guided, you've got bigger chunks of work. Same strategy, it's dynamic, so each thread will get a chunk of work. When it's done, it'll go and get another one, but they start off larger and they get smaller, so it's potentially less overhead with the guided. And just to come back to something that was actually a very good question early on, we typically expect, so the default, if you don't say what a schedule is, most of us kind of expect the default to be static because it's less work, okay? So in many cases, in fact, that is what happens. So if you don't say what the schedule is, you probably quite likely get 1 big chunk. However, in contexts where these are probably not HPC contexts where there's likely to be a fair amount of system noise, what happens? Well, the system could slow a thread down, and if you have an even distribution, so static distribution, and one thread is suddenly going off and doing something for the OS, it's going to be way slow. Everybody waits at the end, so all the other threads are going to be degraded to the same point. So on systems where, and again, this is not your HPC environment per se, but where you have to expect a fair amount of system noise, the default might actually be dynamic, okay? So in other words, you expect that somebody's going to be degraded somewhere, so you take that into account in your default. So don't make assumptions on what defaults are. Check them out and make sure and realize that in different environments, because in fact of the way the environment is set up, you may have different defaults, and they may be very sensible ones, right, for that context. Yes.
So just to make sure that I get this one right, if I have a node with only 8 cores, is the assumption that I'm going to submit more threads than 8?
No. You can try things. It's again very context specific whether it actually makes any sense to do that. It might do.
So if I submit only 8 threads, so exactly the number of cores, and the core is dedicated to me, is there any incentive of actually using the scheduling or not? I mean, on a GPU, yes, there are, because a bit more, and then you try to hide the latency. But what about in this context?
Okay. Yeah, so this is not so much trying to help you decide what number of threads to use per se, but how to divvy the work up among them. And if you have a loop nest where every iteration really has exactly the same amount of work, and if you're not expecting a lot of system noise, then you probably want to go with static because it has very few overheads, right? Each thread computes its own set and does the work. However, if you have a loop nest where the amount of work per iteration varies quite a bit, or you don't know it, then you may well want to go for a more dynamic schedule. Right, so the difference really is here. If you're not sure, if you're not sure that they're all going to take pretty much the same amount of time, you probably want to do something that's either the straight dynamic or guided. So it's really designed to handle less predictable workloads. Is that better? Okay, good. Oh, okay. Sorry.
What is the overhead of dynamic scheduling?
Well, it's very implementation dependent, so you probably test that later, right? Yeah, I think we'll actually even ask you to go and have a look for yourself just to see what you can find. But as you can see, the overheads are going to involve each thread actually needs to. So you have to have a record of what iterations have already been performed and what the next chunk is. So it's not trivial. Yeah, we will say a little bit about overheads later, so we'll come back to that. Okay, so. The parallel loops are probably the most important way of actually distributing iterations among threads, so very fundamental. Another thing that has a long history and is Somewhat less flexible, but when it's useful, it's very useful, are parallel sections. So this is also a fairly old concept in shared memory programming, where you have an OpenMP sections, and then you have a set of, well, you've got 2 or more individual sections, and each of these sections is going to be executed by one thread, not multiple threads, just one thread. And so in this case, you have 3 sections. If you have 3 or more threads, each of those threads will get one section. If you only have 2 threads, one of them will be executing a section and then going back and doing the next one. So it's by design less flexible. Obviously, if you spelled out all these different sections, you have a static number of them, which limits its usefulness, but it can be also very useful. And again, there's also a barrier at the end of this construct. Just to share one quick example of a place we used this one time in a piece of code was actually from the oil and gas industry. It was doing a lot of I/O, and we used sections as one of the ways in which we sort of organized this code. So we had basically a section that was reading in a chunk of data, setting a variable which basically said this data is available for processing. Another thread which actually then once the signal basically was there, so in other words, the data is available, did the data processing, then set another flag to indicate that their work was done, the results are there, and then there was an I/O section. So basically orchestrating this. The problem with that, of course, is that if your work's not balanced, you've just got one thread doing the processing. So one other way to deal with that was actually to create nested parallelism here, and inside that section have another level of parallelism so that there are actually multiple threads doing that work of the processing. Right? So one use of it is if you do have these very distinct kinds of operations going on, even though it is a somewhat limited concept, it can actually be quite useful. All right, a few other things that we have. Master construct. Master, remember the master thread is the one with thread ID 0. You can actually just get the master thread to do something by using the master pragma. Everything else, all the other threads just completely ignore that and race past it. They don't even wait for it. So here you've got some work going on. When the master thread reaches that pragma, it does the stuff and then continues. And the other threads will completely bypass it, which means that if you actually need them to wait for each other, so here in particular, if they're all doing something with the boundary conditions that are being exchanged there, you have to insert a barrier. So we haven't seen this construct before. Something else you can do in OpenMP is set a barrier if you need one where it's not implied.
I actually had a question about sections.
Oh, I'm sorry.
What happens if you specify more threads than you have sections?
Okay, so if there are more threads here, then some of them will be idle, right? Yeah, so it's an inflexible construct because obviously you have exactly whatever number you have, and that has no relationship potentially to the system that you're running on. But again, sometimes, even despite that, it can sometimes be extremely useful. And the one that I showed afterward, the example that I showed actually was quite useful in practice. So, but yes, some of them could be idle. Okay, so the master thread does it. The one with thread ID 0, everybody else just skips it. We have another construct which is very similar, which is single. And single, I hope it sort of is pretty self-explanatory. It says that one thread does it, but it doesn't matter which one. So a typical implementation here, this is just the same piece of code before, would say each thread will do this work, and when it hits the single clause, the thread will check to find out whether it's the first one to get there. And the first one that gets there does the work, and then reaches this. And in contrast to the master, there is actually a barrier at the end of the single. So at the end of single, the other threads, if they're not the first one to do it, they will wait until that update has been performed. Okay, so those are two different ways to ensure that just one thread does some work inside the parallel region. You don't have to exit a parallel region to allow one thread to do something, which is very important. Very quick shortcut. Because they're quite common, you can just use a one-line feature to specify an OMP parallel and an OMP 4 do. And the same thing with sections. So that's just notation. It's syntactic sugar, if you like. There's nothing in there. Okay. One comment that I wanted to make, we talked about this before, I just briefly made the point that if you create a parallel region, you might have the parallel construct in your code, and then you'll call some procedures, maybe a whole bunch of different procedures in there, and some of the actual work sharing features could be inside those other procedures, which is just fine. We call these orphaned directives. We say, oh, it's just a term, you don't have to worry about it too much, but when they're actually in a procedure that doesn't have this parallel specifically inside the same procedure, we call those orphaned directives. And the only reason I'm bothering to say this again is that you could have this little question as well, what happens if I call that procedure from sequential code? Which could happen, right? If I've got a procedure and I'm calling it from inside a parallel region where I have a team of threads executing it, but I could also call the same procedure from some sequential code. That's actually just okay. You're allowed to do that. And in fact, it's not going to be executed, or you can think of it as being executed by a team with just one thread when there are no other threads there. Right, so there's no problem doing that. You can only have to have the one piece of code.